Okay, our topic today is weak acids and weak bases, and our objective is for you to be able to implement their formulas that they have. All right, it's always good to remind yourself of what is an acid and what is a base. An acid is a proton donor, proton giver, whereas a base is a proton acceptor. All right. Now we're going to talk about some general equations because these general equations are going to help us derive all our formulas that we're going to come up with today. A weak acid is often written like this. You've got the proton that's going to lose, and you've got some anion. What does it give its proton to? It gives it to water, and that makes hydronium and leaves the anion in solution. Now, for a base, you've got a base that's dissolved. What do bases do? Bases accept protons from water, all right? And if this water accepts a proton, it's going to become hydroxide, and the base would become BH+, all right? And that's what the general equation for a base is. Now, I want to go back and talk about something real quick. It has to do with this equation. I could also write this equation like this. And I like this because you're taking your conjugate base of the acid in the first equation, and you're using it as a base. It accepts a proton from water like that. All right. And then you can see that these two things are kind of like mirror images of each other. If I were to add these two equations up, I'm just going to be left with the autoionization of water. All right. Which I think is kind of neat. Now, I just want to remind you or show you that here are all these formulas are going to be all that we're on this paper from now on. The ones that we go over from now are going to be on this paper. I was expecting to see the equations that I just showed you, but they're not there. But the next thing is these equilibrium expressions. So your equilibrium expression, if this is my formula, how do I get an equilibrium expression? Well, I eliminate anything that is a liquid or a solid. All right, and there's my liquid. And I use anything else. So that's going to be, and they give this Ka for acid. How much hydronium does it make in the solution? And if this is our base, all right, how much hydroxide does it make would be written or understood from the equilibrium expression of the base. Kb is equal to that. All right. Now, if you go back, there's the two equations. All right. Now, I want to go back to the original two equations that were like kind of mirror images of each other that ended up into all the autoionization energy of water, and talk about the one that's not on the AP reference, mainly this one, and talk about its equilibrium constant. All right, there it is. Now it's written as a Kb because A here, or this anion is acting as a base because it's accepting a proton from water. All right, and the reason I want to show you this is remember this expression. Kw is these two things multiplied by each other. Well, if you'll notice in our Ka expression, all right, our Ka expression, is this, it's got this hydronium ion. So then I can solve this equation for hydronium, and I'm going to get this, all right? Now, you don't need to write this all down. I just want you to know how this thing comes about. And similarly, in our Kb expression, you notice that hydroxide is here, and it's also there, all right? So therefore, I can solve this equation by multiplying by this and then dividing by that to be equal to hydroxide, and I get that. All right? Now what I can do is I can substitute my proportionalities. All right, I just made that, and I can substitute them in here. All right, and now let's see what happens. All right, you'll notice, there. I'm going to rewrite this. Okay, do you notice anything? You might notice that you've got Ha and Ha and A negative and A negative. They're going to cancel out, and I'm going to be left with what? I'm going to be left with the combined equation that Kw is Ka times Kb. All right, so that's one of these combined equations that kind of takes them and uses them together. And the second is if I take the log of them. And remember, Kw is e to the negative 14th. So that's 14 equals pKa plus pKb. All right? And these combine, and so these are my two combined equations if I look at the equilibrium constants of both weak and strong acids. I just want to take a minute to talk about what the things mean. Relate Ka is basically how strong the acid is. The bigger the value, the stronger it is. It's basically another way of expressing the hydronium concentration for an acid. It's just, but it's at equilibrium. Now pKa, it's the same thing as pH, except you're taking a log of a concentration values. Lower numbers on a pKa, it's just like lower numbers on the pH scale. pK or Kb, it's the same thing, and it's the only difference is pKb. The lower numbers still mean stronger base. All right. Now, I think this is a little tricky. So Ka, it's proportional to H3. As numbers go up, acidity also goes up. Now, Kb, it's like hydroxide. It's as numbers go up, alkalinity goes up. All right? And pKa, it's like pH. As numbers go down, strength, I spelt that wrong, goes up. And it's the same thing with pKb and pOH. As the numbers go up, the strength goes up. All right? Okay, going for the W. We have another formula box. It's very similar to the last one. The way to relate Ka and Kb is with Kw. They equal Ka times Kb. All right? And therefore, the log, natural log of these things will give you 14. All right? You're going to use that to go back and forth. And for your pKa's and your pKb's, you're going to use your natural log. All right? And there's our second formula box. All right. I hope this has been helpful, and I hope you have a good night. All right. Bye.